All right, so we're going to finish up Module 15, and then that's really the last of the learning, and everything's going to be preparing for exam, depending on which one you're going to be taking. So we're going to look at the different circuits, series and parallel circuits. So if you think about Christmas tree lights, where you got the string of lights and one goes out and then everything else goes out, that is when the lights are in series. If you have a string of lights, one goes out, the rest do not, then that strand of lights is in parallel. Okay, so in a series circuit, all devices will decease. Okay, so series circuit, all devices will cease to function if one goes out. And because what happens is that when that one goes out, it breaks the circuit, and so it's an open circuit, and the current cannot flow. The parallel circuit, that one allows devices to work independently of each other. All right, so if one stops, the others will still work because the current is, it doesn't break the circuit, and the current is still allowed to flow through them. All right, when resistors are in series, you're going to, their individual resistance will be added together. Okay. And then in doing this, when you basically add more and more resistance, this reduces the current more. All right, when resistors are in parallel, on this, the resistors do not add up individually, or they add up. They don't add up directly. The resistance of two parallel resistors is actually going to be lower than the resistance of one. Okay, and so they do not add directly. And so the way you can think about this is if you had stormwater pipes going under a road, a series of 3 pipe openings here, and this, a creek flowing through. You think about the individual water droplet, it's got to choose which pipe it's going to go through. It's not going to go through all 3 of those pipes, or the electricity, the current is not going to go through all 3 of the resistors. It's got to choose a path. Okay. So the current is higher, and resistance is lower. All right. So looking at a circuit, All right, this is resistors in series. All right, so I have R1, R2, and R3. And so our current is gonna go like that. So in order for the current to get from one side of the battery to the other, it's got to go through all three of the resistors. If one breaks, then everything breaks. And so what we have is the effective resistance. And that is the total resistance replaced by a single resistor. All right. So R effective is going to be R1 plus R2 plus R3, or however many we have there. Let's write that up here. All right, so like I said, this is series. All right, then if we have a parallel circuit, all right, so this would be my R1, R2, and R3, and so the current's gonna go around. But as you see, the current is now going to choose a path as to which resistor it's going to go through. So in parallel, the current, the total current, is I1 plus I2 plus I3, the current going through the individual resistors. Okay. But if we're going to do the resistance and the effective resistance, it is 1 over R effective equals 1 over R1 plus 1 over R2 plus 1 over R3. So you add that up, and then you need to remember to take the reciprocal to get what your R effective is. All right, and so I total is going to be the voltage over R effective. All right, so we're going to do an example. There. All right, so we have a circuit here. R1 is going to be 10 ohms, R2 is 5 ohms, and we want to know what is R effective, and so it's just going to be 10 plus 5, so 15 ohms. On parallel, if we had same resistors, R1 is 10 and R2 is 5 ohms, so here it's going to be 1 over R effective is 1 over 10 plus 1 over 5. That gives you 0.3, that's 1 over ohms. So again, like I said, you need to take the reciprocal of that. And so R effective will be 3.33 ohms. Okay, if there are too many resistors in a parallel circuit, or too few in a series, so too many here, too few there, the circuit can draw too much current. And so the more the current the circuit draws, the hotter it's going to get. If it gets too hot, then a fire can result. And so we use devices to help ensure safety, that wouldn't happen. And that's fuses and circuit breakers. So a fuse is a thin conductor that's very sensitive to heat, and it's encased in glass, and it's into the circuit somewhere. And so the more the current runs through it, the hotter it gets, and if it gets too much current, then it's going to break. And that's what we call blowing a fuse. And so on a circuit, a fuse would be diagrammed like that there. And so then for you to go use the circuit, you've got to replace that fuse. Okay, and with it breaking, it causes an open switch and shuts down the circuit from working. Circuit breakers do the same thing. You've got those in your house, and it's made of material that bends as it heats up, and so the hotter it gets, the more it's going to bend, and then when it gets to a certain point that's predetermined, then the circuit will flip and shut everything off to stop the current from flowing. In that case, like I said, we got blowing the fuse, and we'll say the circuit breaker's been tripped. Okay. All right. So if your fuses keep blowing or your circuit breaker keeps tripping, you've got a problem that you've got to fix. All right. And sometimes it's that the appliance needs to be repaired because it's drawing too much current, or there's too many things plugged into an outlet. All right, so we're going to look at a circuit and analyze how much current should be going through it and what fuse to put on it. Alright, so we've got this parallel circuit. I've got 4 ohms, 8 ohms, and 12 ohms. I want to know how big of a fuse to put on this circuit, and we're looking at our choices of 4 amps, 8 amps, actually 4, 6, or 8. Okay. And then the other thing we want to determine is how much power is going to be going through. So defined are R effective. It's going to be 1/4 plus 1/8 plus 1/12. That gives us 0.46, 1/ohms, and R effective is going to be 2.18 ohms. All right. And so now looking at our equation, V equals IR, we have, I didn't tell y'all this is a 12 volt battery over here. All right, so 12 equals I times 2.18, and I is going to be 5.5 amps. All right, so in this case, we would choose the 6 amp fuse. For obviously, the thing will never work because it'll keep shutting off. 8, we don't want to allow too much because then it will overheat and possibly cause a fire. So 5.5 is what we have. So 6 is a good fuse to put on there. And then if we're looking at the power, we have P equals IV. And so we have our amps of 5.5 and our volts 12. And so we have 66 watts. Okay. One more example. This one is in series. We've got 15 ohms, 10 ohms. This is 120 volt there. And so we're looking at what size fuse. This time our choices are going to be 6, 8, or 10. Alright, so we need to find our R effective, which will be 10 plus 15, which is 25 ohms. Then V equals IR, so 120 equals I times 25, and the amps is going to be 4.8. Alright, so 4.8, we want to use the 6 amp fuse. Again, if we do the power on this one, E equals IV. And we've got, where'd it go? 4.8 amps and 120 volts. And multiplying that, we have 576 watts. Alright, so we've done circuits in series and we've done them in parallel. Now we're going to do complex circuits, where we put series and parallel together. All right. So I have 6 volt battery source, got 10 ohms, 4 ohms, 8 ohms, and 25 ohms. And what I'm looking for is power. Okay, that's our end result here. Alright, so the first thing I want to do is I want to take this parallel system right here and get R effective for it. And so for that, it's going to be 1 over R effective is 1 over 8 plus 1 over 25. That is 0.165. And so R effective is 6.06 ohms. And that is for these two, this parallel system right here. So in essence, I could redraw this circuit. So the 6 volts, I've got my 10 ohms. I have my R effective representing here 6.06, and then the 4. And now everything is just in series, and I can just add up those resistors. 10 plus 606 plus 4. And so I've got 2006 ohms. All right, so I need to find my current. So V equals IR, and we have 6I 20.06, and I is going to come out to be, it's like 0.3 amps. All right, power is what we're looking for, so P equals IV at 0.3 times 6, and so the power is 1.8 watts. All right, we're gonna do one more circuit, and it's a little bit harder, but if you just take each piece, it's, you'll see that's really no big deal. All right. All right, I have 120 volts there. I'm just gonna call each number, each grouping here. We've got 10 ohms, 25 ohms, 50. This one's 100, 15, and 7. All right, so what we want to do is figure out our effective for each of these little parallel clusters here. Okay, so of the first one, this is 1 over, because this is parallel, 1 over 10 plus 1 over 25. And our effective is going to come out to be 7.14 ohms. We do the same thing over here for our effective 2. So 1 over 50 plus 1 over 100. All right, add that together, then take the reciprocal. This is going to come out to be 33.3 ohms. And then my last one down here, so 1 over 7 plus 1 over 15, and our effective is going to be 4.77 ohms. So now basically I've reduced everything to in series with my R effectives. So we get an overall R effective of 7.14 plus 33.3, 4.77. And it's going to be 45.21 ohms. All right, again, we're looking to look for power here. First thing we need to do is find our amps. So V equals IR. We've got the voltage of 120, and I times 45.21. I comes out to be 2.65 amps. And so then we're going to take that and do the power equation. So again, it's 2.65 amps, 120, and the power is 318 watts. And that is everything. Alrighty.